Did you know that gravity isn't the same everywhere on Earth? Yes, you heard it right. In some places, you'd weigh less than you do right now. Welcome to the intriguing world of gravitational anomalies, where the fundamental force that keeps us grounded takes on a surprising twist. Now, if you're imagining gravity as a consistent, unchanging force, you're not alone, but in reality, it's anything but. Earth's gravity isn't uniform. It varies from place to place. Picture this. If you were to hop on a scale at the equator, then jet off to the North Pole and weigh yourself again, you'd find you're slightly heavier at the poles. That's right. Your weight can change depending on where you are on Earth, and it's all due to gravitational anomalies. But what causes these gravitational fluctuations? The answer lies in the Earth itself. Our planet isn't a perfect sphere. It's an oblate spheroid, bulging at the equator and squashed at the poles. This irregular shape causes gravity to be stronger at the poles and weaker at the equator. Altitude also plays a role. The higher you are, the further you are from the Earth's center, and the weaker the gravitational pull. So, if you've ever dreamt of shedding a few pounds instantly, just climb a mountain. And let's not forget about the Earth's diverse geological features: massive mountains, deep ocean trenches, dense rock formations. All of these can cause local variations in the gravity field. And sometimes, these variations can be quite significant, leading to what we call gravitational anomalies. These anomalies aren't just terrestrial. They exist beyond our planet, on the Moon, Mars, and even in the far reaches of space. They are silent reminders that gravity, the force we take for granted, is more complex and fascinating than we often realize. So, let's dive deeper into this fascinating world of gravitational anomalies. You might think that the larger an object is, the stronger its gravitational pull. However, that's not always the case. The gravitational force an object exerts isn't solely dependent on its size. Enter density, a major player in the gravitational game. Imagine a feather and a lead ball of the same size. It's easy to assume that they would exert the same gravitational pull, right? But in reality, the lead ball, being denser, has a stronger gravitational force. This is because gravity is determined not just by size, but also by the amount of matter packed into a given space. So, while size does have a role to play, it's not the be-all and end-all. The denser the object, the more mass it has in a given volume, and the stronger its gravitational pull. It's a cosmic dance of size, density, and gravity. So size isn't everything when it comes to gravity. Ever heard of the Hudson Bay anomaly? Here, gravity is significantly weaker than other parts of the Earth. In the vast frozen expanse of Canada's Hudson Bay, there's a gravitational oddity that's been puzzling scientists for decades. This region has less gravity than any other part of the world. Now, that doesn't mean you'd float away if you set foot there, but there's a noticeable difference if you were to weigh yourself on a scale. So, what's behind this enigma? Well, it's all about the land, or rather, the lack of it. You see, the Earth isn't a perfect sphere. It's more like a slightly squashed ball, bulging at the equator and flatter at the poles. This uneven distribution of mass results in variations in the strength of gravity around the world. But the Hudson Bay anomaly is a little more complex than that. One theory points to the Laurentide ice sheet, a colossal glacier that covered much of North America during the last ice age. This ice sheet was so heavy that it pushed the Earth's crust down into the semi-fluid mantle below, displacing the land mass. When the ice melted around 12,000 years ago, the land began to spring back, a process known as isostatic rebound. But the crust hasn't fully returned to its original position, and less land mass means less gravity. Another theory involves convection in the Earth's mantle. Beneath the crust, the mantle's molten rock slowly churns in circular currents, and some scientists believe these currents have been slowly whisking mass away from underneath the Hudson Bay area, thus reducing the gravity. However, despite these theories, the Hudson Bay anomaly remains a subject of ongoing research. Scientists are still piecing together the puzzle, using data from satellites and ground-based measurements. The Hudson Bay anomaly truly is a gravity-defying mystery. The moon isn't just home to craters and Neil Armstrong's footprints. It also hosts some strange gravitational anomalies. Now, let's dive into the shadowy depths of lunar mass concentrations, known more commonly as Mascons. These Mascons are intriguing regions on the moon that boast a stronger gravitational pull than other areas. The story of their discovery is an interesting one. In the mid-20th century, scientists noticed that the orbits of spacecraft flying over the moon were unexpectedly changing. It was as if the moon was reaching out and tugging on them a little stronger in certain spots. After much head-scratching and data crunching, they pinpointed the cause to these Mascons, regions of the moon with a stronger gravitational pull. So, what's the deal with these Mascons? How come they have more gravity? Well, it all boils down to density. These areas are denser than their surroundings, and as we've learned, more mass means more gravity. But why are they denser? That's where the plot thickens. One theory suggests these Mascons could be remnants of heavy lunar lava that filled the craters created by ancient asteroid impacts. Over time, these lava pools cooled and solidified, sinking into the moon's crust and creating a denser region that pulls harder on anything passing overhead. Another theory proposes that these Mascons are the result of the moon's crust and mantle compacting following an impact. The intense pressure from an asteroid strike could have compressed the lunar rock, creating denser regions that exert a stronger gravitational pull. But here's the kicker. We still don't know for sure. Despite decades of study and numerous lunar missions, the exact cause of these Mascons remains shrouded in mystery. Our moon, it seems, is not just a silent sentinel in our night sky. It's a celestial body with its own set of intriguing gravitational secrets. Even our moon holds gravity secrets, it seems. The journey into the enigmatic world of gravitational anomalies is far from over. Stay tuned for more astounding revelations as we venture to the towering peaks of Mars Olympus Mons next. Mars Olympus Mons, the tallest volcano in our solar system, also exhibits a gravitational anomaly. When we think of Mars, we often picture its red, dusty landscape and perhaps the small rovers that have been sent there to explore. But Mars has a secret, one that's towering above everything else on its surface. That secret is Olympus Mons, the tallest volcano in our solar system. Standing at a staggering 13.5 miles high, it's nearly 3 times the height of Mount Everest, the tallest peak on Earth. But Olympus Mons isn't just notable for its size. It's also home to a fascinating gravitational anomaly. You see, gravity isn't as straightforward as you might think. It's not just about how massive an object is, but also how that mass is distributed. And Olympus Mons, with its enormous mass concentrated in a relatively small area, has a profound effect on the gravity around it. Think of it like this. Imagine you're standing on a trampoline. The trampoline is Mars's surface, and you are Olympus Mons. Your weight causes the trampoline to sag, creating a dip or a well. That's what Olympus Mons does to Mars's gravity. It creates a gravitational well, a region where gravity is slightly stronger. What's truly fascinating is how this affects objects in orbit around Mars. Satellites, for instance, experience a slight tug as they pass over Olympus Mons, causing them to dip in their orbits. This dip is detectable and measurable, providing a unique way for scientists to study the volcano and its gravitational effects from millions of miles away. Gravity, it seems, is a bit of a show-off. It's not content to just hold us down on Earth. It's out there in the vastness of space, making its presence known in the most dramatic ways. From the highest peak on Mars to the deepest depths of our oceans, it's always there, influencing our world and others in surprising and mysterious ways. It appears gravity likes to play tricks in the most unexpected places. Our Sun, the powerhouse of our solar system, has a stronger gravitational influence than you might think. Picture a celestial dance where the Sun, in all its fiery glory, leads the waltz, dictating the rhythm and the moves of its planetary partners. This is the reality of our solar system, where the Sun's gravitational pull choreographs the orbits of the planets, keeping them in line and in motion. But it doesn't stop there. The sun's gravitational reach extends far beyond the planets, influencing the paths of comets, asteroids, and even the trajectory of spacecraft. Comets, those icy bodies that originate in the farthest reaches of our solar system, are drawn in by the sun's gravity, which shapes their orbits and brings them into our visual field. Their spectacular tails, a result of the sun's heat, are always pointed away from the sun, a testament to the sun's influence on even the smallest particles. Asteroids, too, are not immune to the sun's gravitational pull. These rocky remnants from the early solar system, primarily found in the asteroid belt between Mars and Jupiter, are kept in check by the sun's gravity. Any deviation from their usual orbit, often caused by collisions, can send asteroids hurtling towards the sun or even towards Earth. Now, let's consider our spacecraft. Ever wonder how they navigate the vastness of space? The answer is gravity assist, or slingshot effect. This is a space navigation technique where a spacecraft uses the gravity of a planetary body, like the sun, to alter its speed and trajectory. This technique allows us to save on fuel, making long-distance space travel feasible. In this grand cosmic ballet, the sun, with its massive gravitational influence, is the prima ballerina, leading and guiding all its celestial partners. It's a constant reminder of how interconnected everything in our universe is and how the sun's gravity truly keeps us all in check. The sun's gravity truly keeps us all in check. Dark matter and dark energy, the universe's most elusive substances, also play a role in gravitational anomalies. These unseen actors of the cosmic stage account for a staggering 95% of the universe's total mass and energy, yet their nature remains shrouded in mystery. Dark matter, despite being invisible and intangible, exerts a gravitational pull, influencing the motion of galaxies and galaxy clusters. It's like a silent puppeteer, pulling the strings of celestial bodies and shaping the cosmic web. Scientists postulate that dark matter might consist of undiscovered subatomic particles, but no one has been able to detect these particles so far. Dark energy, on the other hand, is a force that's pushing the universe apart, causing its expansion to accelerate. Think of it as an anti-gravity, a repulsive force that defies our conventional understanding of physics. While we can't see or touch it, we can observe its effects on the cosmic scale. It's this dark energy that's believed to be responsible for the warping of space-time, a concept that Einstein first introduced in his theory of general relativity. This warping, or bending of space-time, is what we perceive as gravity. Massive objects like stars and galaxies curve the space around them, creating a sort of well that smaller objects fall into. Now, imagine dark matter and dark energy, with their invisible hands, further twisting and stretching this cosmic fabric. These manipulations can lead to gravitational anomalies, where the force of gravity behaves in unexpected ways. So, while we might think of gravity as a constant, unchanging force, it's actually a dynamic and complex phenomenon, influenced by the visible and the invisible, the known and the unknown. It's a cosmic dance between matter and energy, light and dark, pushing and pulling in a never-ending ballet. These dark entities add another layer of complexity to our understanding of gravity. They remind us that there's so much more to learn, so many more mysteries to unravel in this vast cosmic playground we call the universe. As we've seen, gravity isn't as straightforward as it seems. This mysterious force that keeps us grounded, quite literally, is more than just an invisible tether to our planet. It varies across the Earth, influenced not just by mass, but also by density. In some regions like Hudson Bay in Canada, gravity is surprisingly weaker. This anomaly, known as the Hudson Bay Anomaly, is attributed to the loss of ice mass from the last ice age, resulting in a decrease in gravitational pull. Our journey took us beyond Earth to the Moon, where we discovered massive concentrations of mass, known as Mascons. These Mascons, located beneath lunar basins, cause gravitational anomalies that have given many a spacecraft a gravity-assisted slingshot, sometimes with unforeseen consequences. On Mars, the highest volcano and the largest shield volcano in the solar system, Olympus Mons, presented its own gravitational puzzle. This towering behemoth, standing thrice the height of Mount Everest, surprisingly doesn't cause a significant gravitational anomaly. Its spread-out mass evenly distributes the gravitational force, keeping the anomaly in check. We also touched upon the Sun's influence. This fiery celestial body, despite its distance from us, significantly influences Earth's gravity. Its gravitational pull causes the ebb and flow of ocean tides and even affects the orbits of planets. Finally, we delved into the dark side of the universe, exploring the enigmatic dark matter and dark energy. These unseen forces make up a staggering 95% of the universe and play a crucial role in the cosmic gravitational field. So we see, gravity isn't just a simple pull towards the center of Earth. It's a complex interplay of forces and factors, some of which we are only beginning to understand. It's a journey of discovery that continually challenges our understanding of the universe and our place within it. So, next time you feel heavy, remember, it might just be a gravitational anomaly. Having journeyed through the cosmic labyrinth of gravity, we hope you found a new appreciation for this omnipresent yet invisible force that shapes our universe. If you've learned something new from this video, or if you're just a fan of fascinating facts, we'd love for you to give this video a thumbs up. Your likes help us reach more curious minds like yours, and we value your support. If you have any thoughts, questions, or your own theories about gravity, we'd love to hear them. So, don't hesitate. Leave a comment below. And remember, the gravitational pull of knowledge is strong, so don't resist. Hit that subscribe button for more content that's out of this world. Finally, if you think a friend or family member would be intrigued by the gravitational mysteries we've explored today, do share this video with them. Who knows? You might just spark a lifelong fascination with the cosmos. Until next time, keep looking up and keep questioning.